In my previous video where I talked about making carboxylic acids from amides, if you go back to that video, you'll see that the main purpose of that reaction was to generate a carboxylic acid. That's what we were after. But take a closer look. What was the second product that was formed as well? It was an amine. And sometimes you want to make an amine, not the carboxylic acid. So there's a very famous reaction called the Gabriel synthesis reaction, in which you're going to take an amide and you're going to convert it into a carboxylate, but the product that you really want is a amine. And with the Gabriel synthesis, there's something to remember, that it's mainly used for primary amines. If you want to make a primary amine, your first thought could be, hey, Gabriel amine synthesis. And so this reaction takes a molecule that looks like this. Like that. And that's called phthalimide. Oh, I'm forgetting one hydrogen right there. Okay. That's phthalimide. Let's spell that right here for you. Okay. When you take phthalimide and you treat it with a strong base like potassium hydroxide, and we could do that in ethanol. And then step 2, treat it with a alkyl halide. Now that's the key right there, is that it needs to be a primary alkyl halide in order to make a primary amine. So after you treat with that, you're going to get something that looks like this. Whoops, I'm adding too many carbons here. Let's do it like that. There we go. And can you get an idea of what's happening here? Do you see what I did? The 2 carbons right here in the alkyl halide, I've now added to that nitrogen atom in the amide. And then you treat that product right there with potassium hydroxide and water again, or potassium hydroxide and water. Okay. And that's going to do the reaction that we are familiar with from the previous video, where you take a amide and treat it with base. Do you see how that's just a amide? And so what that's going to do is it's going to go through the same mechanism that we went over in the previous video, and we're going to generate two carboxylates right there. But that's not what we're after. If we were after this species, we would take this and treat it with acid and isolate the carboxylic acid. But we don't want the carboxylic acid in a Gabriel synthesis. We want the amine. The other piece, or the other product that's generated, is a primary amine. So it's going to be this piece right there. Let's move that plus sign over here. So you see how this right there is that right there. And we generated a primary amine. Now I know I've already said this, but I want to say it again just to make sure you understand how important it is. When you're doing the Gabriel amine synthesis, you're just generating primary amines. And the reason why is if you try to generate a secondary amine by using a secondary alkyl halide, there's going to be an elimination competition, and you're not going to get a very good yield of the amine that you actually want. So that is the overview of what happening. So now let's look at it in more detail by looking at the mechanism. So in our first step here, we are going to do a proton transfer, in which we're going to use our potassium hydroxide. I'll just represent it as the hydroxide. And we're just going to do a proton transfer like so. So that's going to generate negatively charged species plus our water that we just generated here. Okay? So we've done a proton transfer. And now we're going to do a SN2 with the alkyl halide. So if we draw our alkyl halide like so, we'll just do an SN2 style. We'll take some lone pairs, backside attack. That's going to generate this species right here. And I'm going to get cut off on the board here. So let's see. We can see it still. That's okay. And then we still have the bromide floating around there as a spectator ion now. So now what we're going to do is add some more, have some base added again. We're going to add the potassium hydroxide and water here. Now what's going to happen here is the same mechanism that we've seen from the previous video where we were making carboxylic acids with amides. So that is where we take our hydroxide, okay, and that's going to come in. Let's see here. Let's go right here, okay, like that. And so there's our nucleophilic addition step. Nucleophilic addition step right there. So we would get something that looks like this. No, not double bonded O. Our OH came in and our turns it into that. Okay. So there's our nucleophilic addition step. Let's see. Then what's the next step? That would be the nucleophile elimination. Nucleophile elimination step, where those electrons are going to come down and collapse back down and then break the carbon-nitrogen bond. And so we would have, we just generated carboxylic acid, and I'm going to extend out that right there. Okay. That already had a lone pair, so now it has another. So that's going to be negatively charged like so. Okay. Now we can envision a intramolecular proton transfer if we'd like. That's not too terribly important, other than there's going to be a proton transfer. We generated a carboxylic acid. We have base present. We have this base right here. Eventually, we're going to just to keep it simple here, we will say we'll do an intramolecular proton transfer here. Okay. So we're doing it irreversible proton transfer, really. Let's see, my marker's getting really squeaky. Let's see if I can find a less squeaky one. Okay. Not really. There's that. And then we've generated our carboxylate right there. Okay. Now we still have a lot of base present from this going right here. So what we're going to do is do it all over again. Because what do we have here? We have an amide. So we're going to do that again. And so I'm going to keep going in a cyclic fashion. So I'm going to erase this to give us some more room now. We'll just keep going around the board. So we do it again. All right, so we have our base. So same concept again. It's going to come in, do our nucleophilic addition step. It's going to come in like that. O minus. We have our NH like that, and the hydroxide came in from that side. And this piece was already there, like that. Then we're going to do another nucleophile elimination. Nucleophile elimination step. That collapses down. The amine leaves. Going to get this piece. We generate another carboxylic acid. That's already the carboxylate. We generated the amine right here. So that's negatively charged. So you can see an irreversible step again, where we are going to do another proton transfer. We're going to do another proton transfer. So if we expand out that hydrogen there, like that, you can see that we can take a lone pair here, do our proton transfer to generate our product. And so I will draw the product down here so we can see it. So our product is going to be down here. So we're going to have a molecule with 2 carboxylates, like that. And if you wanted to isolate a dicarboxylic acid, you would treat that species with acid and protonate. But we don't want that, because what else is another product here? That would be the primary amine. And that's what we wanted. That's what the Gabriel amine synthesis is all about. And so that's how you do it. Now, to fully appreciate why this reaction is so cool and useful for generating primary amines, you have to go back, well, way back to some previous videos that I've made, or if you remember doing a reaction like this. What if we took a primary alkyl halide and treated it with ammonia, okay, like that? And what would you get? Our hope and our design is that we want to get that as our product. Okay? We just want to have it do a simple SN2 and a proton transfer type thing to get us to our product. Okay, so after that first SN2, we would have that, and then you do a proton transfer to generate your primary amine. Okay? But the problem is that you still, when you generate that primary amine, that's a base. So that primary amine can react with the starting material. And so you're actually, if you do this reaction right here, you're not going to generate just the primary amine, but you are going to generate, so let's do step 1. Step 2 is a proton transfer. mechanistically here, we would get a mixture of this. Like that. And you get, so there's our primary amine, there's our secondary amine. You would get something like a tertiary amine and even a quaternary amine. See, so if you try to do it this way, you're going to get a mess. And your yield right here for your desired product, the primary amine, is not going to go so well. That's why the Gabriel amine synthesis is so powerful. It's because it doesn't generate these guys right here, just our primary amine. So that's pretty cool.